The C++ standard template library, it's just amazing, right? It gives us this huge toolbox of data structures, ready to go. But, with all that power comes a big question. Which tool do you actually pick?
Yeah, so let's get right into it. You're staring at your screen, you need to store some data, and the STL rolls out this massive buffet of containers: vector, list, map. And you know that picking the wrong one can absolutely tank your performance, or just make your code a total mess to deal with later. So, how do you even begin to choose?
So, here's our game plan for this explainer. We're going to build a super simple framework to make this decision easy. First, we'll look at the core problem itself, then the two containers you should be reaching for most of the time. We'll cover when those defaults don't work, how to write cleaner code with them, and finally, we'll touch on what happens when you throw threads into the mix.
All right, the first and honestly, the most important thing to get right is this: stop thinking about the containers for a second. Instead, think about what you actually want to do with your data. Seriously, are you just going to access stuff by its position? Are you searching for things with a key? Or are you constantly adding and removing things from the front and back? Your intent is everything.
And this is a point that Philip Johnston from Embedded Artistry makes perfectly. He says, the most important aspect to consider is what you intend to do with your object. Think about it. If you need a stack, last in, first out, using standard stack shouts that from the rooftops. It tells everyone, including your future self, exactly how this thing is supposed to be used. It's all about clarity.
Okay, so what's really wild about all this is that even with all these options, for the vast majority of cases, I'm talking like 80% of the time, maybe even more, your choice really just boils down to two containers. Just two. If you can get this part right, you're already way ahead of the game in writing solid C++. And here they are, the two workhorses. For anything that's a sequence of things where you care about the order and position, your go-to, your default, should be std vector. And for anything that's a lookup, like a dictionary, where you use a key to find a value, your default is std unordered_map. That's it. Start there. So what's the big deal with std vector? Why is it the default? Well, it all comes down to its secret weapon, its memory layout. See, std vector stores all its stuff in one single continuous block of memory, just like an old school C array. And for modern CPUs, this is pure gold. It's all about the cache. When the processor needs one element, it doesn't just grab that one thing. It grabs the whole neighborhood and sticks it in the super fast cache. This makes looping through a vector just ridiculously fast. But, defaults aren't a silver bullet. They don't work for everything. So what if you need to be adding and removing stuff from the front of your sequence all the time? Or what if you actually need your key value pairs to be sorted? This is where things get a little more nuanced, and we need to look at some of the other specialized containers. And this slide is basically your cheat sheet for those special cases. If you need to add and remove from both the front and the back, STED-DQ is your guy. If you're doing a ton of insertions and removals right in the middle of a huge collection, STED-LIST might be what you need. We'll come back to that one. If you need sorted keys, that's when you grab STED-MAP. And if you need to store multiple values for the same key, well, that's what the multi-versions are for. Okay, but let's put a huge asterisk next to std-list. You'd think it'd be great for middle insertions, right? Well, as the legendary Bjarni Strastrup has pointed out, on modern machines, std-list can be shockingly, painfully slow. Why? Because every single element is in a completely different spot in memory. To get from one to the next, the CPU has to jump all over the place, chasing pointers. This just completely wrecks cache performance. It's so bad that often just eating the cost of a standard vector insertion is actually faster in the real world. Crazy, right? And that brings us to the big trade-off for our key-value containers. It's a classic battle: std map versus std unordered map. std map is all about order. It uses a tree structure to keep your keys perfectly sorted. This gives you lookups in logarithmic time, or O log n. But std unordered map, it uses a hash table. It completely gives up on order in a quest for pure speed. And it gets it, giving you constant time, O1, lookups on average. So the rule is simple. Unless you have a really, really good reason to need sorted keys, you want the speed of unordered map. Okay, so we've picked the right container. Awesome. But now what? How do we actually work with the data inside? For years and years, we've just written manual loops for everything. But modern C++ offers us something so much better, a more powerful and, frankly, more elegant way to handle our data. And this quote from a developer on Reddit just hits the nail on the head. They're talking about that old STL algorithm syntax and how frustrating it can be. You know the look. To do something simple like filter some data and then transform it, you end up with this verbose mess of iterators and temporary variables. It's so clunky that sometimes you just give up and write a plain old for loop because it's easier to read.
And this slide shows you exactly what that developer was talking about. This was the problem. The algorithms just didn't chain together nicely. If you wanted to, say, filter out some elements and then do something to the ones that are left, you had to save the filtered results into a whole new intermediate container. It's wordy, it's inefficient, and it allocates extra memory you don't really need.
But then came C++20 and ranges, and it completely changed the game. Just look at this. The new way is all about building a pipeline. You take your input, you pipe it through a filter, you pipe that through a transform. It's just one single beautiful line of code. Not only is this way easier to read and understand, it's also way more efficient. It processes the elements as they go, so there are no intermediate containers, no extra memory allocations. It's just better.
So, we've picked our container, we're using slick, modern algorithms, we're feeling pretty good. But then, someone mentions multi-threading. What happens then? Because the standard library containers are by and large not safe for multiple threads to write to at the same time. And this, my friends, is where a whole new world of bugs can open up. The monster we're trying to avoid here is called a data race. Now, here's the formal definition, but let's just boil it down. It's simple. If you have one thread trying to write to a piece of memory at the same time that another thread is either reading or writing to that exact same spot, and there's nothing in place to coordinate them, you've got a data race. And a data race in C++ means undefined behavior, which are basically the two scariest words in the entire language. This visual shows you exactly why this is so scary. Take a look at that middle example. Thread A reads the value of x, which is 44. But before it can write its result, the system switches to thread B, which also reads x as 44. Then thread A wakes up and writes its result, 54. But then thread B wakes up and writes its result, 32, completely blowing away the work thread A just did. The final result is just wrong. One of the updates was completely lost. It's chaos. Now, the classic solution to this problem is using locks, or a mutex. But as this great advice from a CERN lecture points out, locks should be your last resort. The absolute best way to deal with this is to design your code so you don't need them at all. Maybe each thread gets its own copy of the data. But if you must use a lock, the rules are straightforward. Hold it for the shortest possible time, never call code you don't control while holding a lock, and be super careful about how you use them. And that brings us right back to where we started. Yeah, the world of C++ containers can feel like a lot. The differences can be subtle and the trade-offs are real. But it's not impossible. If you start by thinking about your intent, default to vector and unordered underscore map, and then really understand the specific reasons why you might need something else, you can cut through all that complexity and make great choices. So that brings us to the final thought I want to leave you with. Take this framework and apply it. I mean, right now. Think about the project you're working on. Is there a std list in there that's secretly killing your performance? Are you using as std map when you don't actually care about the order? Because, as we've seen, sometimes a small, simple change in your choice of container can make a massive difference in your code.